For today's notes, we're looking at combinations of functions, and combinations are very basic, and that's going to build up and lead into compositions of functions. So what we're looking at initially is adding, subtracting, multiplying, dividing two functions together the same way we would any two integers that we may be given. When we go into combinations of functions, we're talking about placing a function inside of another function and generating a whole new function through that method. So there are a couple of quick examples right here. We can see we have the sum, the difference, product, and the quotient. The sum, you just take two functions, you add them together, you combine like terms, and you're done. You've created a new function, in this case f of x plus g of x. With the difference, you're doing a very similar process. You're taking f of x minus g of x, and you combine like terms in the same fashion, and you generate the function that way. And then the product, you multiply them together. In the case of the example shown here on the screen, you would use the FOIL method to distribute and multiply those terms together. And then finally, there's the quotient where we do division. This one doesn't simplify any further. It's just simply the function f of x over g of x, and that's all you can do. The domain of these functions, for when we're talking about the sum, the difference, and the product, the domain is going to be the intersection of the domains of the functions that we're combining. So whatever they have in common, that's the domain of the new function. The only other difference applies to the quotient, and that's where we also have to consider that the denominator, whatever the function might be in the denominator, it also cannot be equal to 0. So we're going to see a few of these in example. Actually, we're going to see a lot of examples in this set of notes. So here is just a kind of a note to give you a breakdown of the sum, difference, product, and quotient, and expose you to the different types of notation. So the sum can be written in either one of these two ways. You can have the f plus g in one set of parentheses of x, or you can simply have f of x plus g of x. And then the same thing goes down through with difference and product. The quotient is pretty straightforward. It's always just going to be f of x over g of x. So let's look at our first example where we're given f of x is equal to 2x plus 1 and g of x is equal to x squared minus 2x, x squared plus 2x minus 1. And we want to find f plus g of x. So looking at our notes, remember f plus g of x is the same as f of x plus g of x. So we take function f, which in this case is 2x plus 1, and we add function g, which is x squared plus 2x minus 1. And all we do now is combine like terms and simplify. So 2x plus 2x gives us 4x. Positive 1 and negative 1 will reduce to 0, and the only thing we have left is x squared. You can leave your answer in this form. My OCD will not allow me to leave answers like that. I always rewrite it in descending orders of power. So either one of these two answers is fine. 4x plus x squared plus 4x. But that's just the simple addition of two functions. With example 2, we're using the same functions as the previous example. Same f of x, same g of x. We're going to find the difference function, and then we're going to evaluate the difference function at x is equal to positive 2. So let's first begin with the notation. It's f of x minus g of x. F of x is 2x plus 1. When you're doing the difference, what I highly encourage you to do is once we get to that minus sign, the next function, place it in parentheses. Because that will help you understand that negative has to distribute through the parentheses. So we have 2x plus 1 minus x squared minus 2x plus 1. Now we can combine like terms. 2x minus 2x is 0. Positive 1 and positive 1 is 2. And then we have that minus x squared. So again, I'm going to rewrite this as negative x squared plus 2. But either one of those answers is going to be correct. Oh, almost forgot. Then we want to evaluate the difference when x is equal to positive 2. So we can take our difference function that we've created, and now we just simply replace x with positive 2 and we simplify. So 2 squared is 4. We have the negative outside the parentheses, so that's negative 4 plus 2, and that's going to be equal to negative 2. So that's the function evaluated at positive 2. Example 3, we're finding the difference quotient, f over g and g over f, and then we want to find the domains of f over g and g over f. So I'm going to do f over g over here on the left in purple, and function f is the square root of x over function g, which is the square root of 4 minus x squared. Now we have a radical in the numerator and a radical in the denominator. What I like to do is rationalize the denominator. It's not good mathematical practice to keep radicals in the denominator, so we do what we call rationalizing the denominator. So in this case, I'm going to multiply the numerator and denominator both by 4 minus the square root of 4 minus x squared. And then when I simplify this, I have radical x times radical 4 minus x squared over 4 minus x squared. So when we do that multiplication, we lose the radical in the denominator. In the numerator, what we may see that we have is the square root of 4x minus x cubed over 4 minus x squared. So there is our new function, that's f over g. The only thing that we have to look at now is find the domains of f over g. And in this case, we need to consider both the numerator and the denominator. First, in the denominator, we have 4 minus x squared. That will factor into 2 plus x and 2 minus x. And if we set both of these factors equal to 0, the first one will tell us that x is negative 2, and the second one will tell me that x cannot be positive 2. So those are my domain restrictions from the denominator. From the numerator, remember the radical has to be greater than or equal to 0. So we're going to set this numerator 4x minus x cubed greater than or equal to 0. And I can factor an x out of both terms. And then we just need to find what makes this statement true. So the first thing we have is the zero product property tells me that the first factor is x is greater than or equal to 0. The second factor tells me that you'll notice this is the same as the denominator on the left, so we can factor that, and it's going to be 2 minus x is greater than or equal to 0, and 2 plus x is greater than or equal to 0. So in both cases, the first one I would subtract 2, divide by my negative, and I would get x is less than or equal to positive 2. On the right, I get x is greater than or equal to negative 2. So there's my domain restrictions for, whoops, I did not mean to cross that out, for f over g. X can't be negative 2, it can't be positive 2, and x has to be less than positive 2 but greater than negative 2. So when we put that together, the domain is x such that negative 2 is less than x is less than positive 2. If you're wondering why I didn't put the equal sign underneath those, it's because of this domain restriction down here on the left. It cannot be negative 2 and it cannot be positive 2. So this function only works for any x values that are between negative 2 and positive 2. The next function that we want to evaluate is g over f. And g over f is just going to be the reciprocal of what we started out with in the first part of this example. And again, we're going to rationalize the denominator. And what we end up with is so looking at this, now we can see The denominator obviously cannot be 0, so x cannot be equal to 0. And in the numerator, we have the same scenario going on as we did in the previous example. X has to be less than or equal to 2 or greater than or equal to negative 2. So in this case, our domain will include positive and negative 2, but it won't include 0. So we could have negative 2 less than or equal to x less than or equal to 2, but x cannot be 0. If you're doing it in interval notation, then you would have a bracket, negative 2 to 0. That would be a parenthesis. Union 0 to positive 2. And then now we get into our compositions of functions. And this is where we're talking about placing a function inside of a function. And this can sometimes get a little bit confusing. Again, there's two different types of notation that you may see. They're both read the same way. They're both read f of g of x. One just has the circle notation on the left. The other one has the parenthetical notation that you see on the right. And rather than talk about it, I'm just going to go through an example, and hopefully this will make more sense to you. So what we see in part A is f of g of x. That means we're taking function g and placing it inside of function f. Remember from the green box above, it's the same as f of g of x. So just as if g of x were a numerical value, let's say g of x was 2. So instead of saying f of g of x, this may say f of 2, and that would just tell me that I put 2 in for every instance of x in function f. Well, with the composition notation, this means that for every instance of x inside of function f, I'm going to replace x with whatever g of x is equal to. So in this example, g of x is equal to 4 minus x squared. So I replace x with 4 minus x squared. And then the remainder of function f is that plus 2. And then I just simplify. I have 4 minus x squared plus 2. 4 plus 2 is 6. So I get 6 minus x squared, or negative x squared plus 6. So either one of those will be a sufficient answer. For part B, notice that we reversed it. Now it's g of f. So we're replacing function f inside of function g. So function g starts out as 4 minus x squared, but we're replacing x with function f. And this is what we end up with. Now we have to expand the x plus 2. So recall that's x plus 2 times x plus 2. And that's going to give you 4 minus x squared plus 4x plus 4. Distribute to negative. Our positive 4s will cancel, or our positive 4 and our negative 4 will cancel. That reduces down to 0. And all we're left with is negative x squared minus 4x. And then finally for part C, it says evaluate g of f of 4, or of negative 2. So we just take what we did in part B, this is g of f, and now we replace x with negative 2. So we have negative, replace x with negative 2, and replace x with negative 2 again. Negative 2 squared is 4, but we have that negative outside the parentheses. Negative 4 times negative 2 is positive 8. Negative 4 plus 8 is 4. So there is a quick example of how to do composition, just simply placing a function inside of another function. Our next example, number 5, it says given that f of x is equal to x squared minus 9 and g of x is equal to the radical, or the square root of 9 minus x squared, find the composition f of g of x. So we're taking function g, placing it inside of function x. Why are my notes so messed up? I don't know what happened there. But I'm going to do this composition here in the middle anyway. Because really this should start a new paragraph down here. So I'll read over that in a minute. Let's focus on the composition. So we're taking function g and we're placing it inside of function f. So that would be the square root of 9 minus x squared, because x is squared right here, minus 9. When we square root, the square root just disappears, essentially. 9 minus 9 is 0. What we're left with is negative x squared. And the domain of this function is all real numbers, because we can place any x value into this function and generate a individual y value. So we have a domain of all real numbers. Now, where the typesetting got messed up, what we would say now is in the previous two examples, so that would be examples 4 and 5, we formed a composition of two functions. In calculus, it's also important to be able to identify what functions are used to create a certain composition of any two functions, or 3 or 4, whatever the case might be. So let's consider right here in the middle of our screen, we have h of x is equal to the quantity 3x minus 5 cubed. We can break that apart into individual functions, and we can see that we could separate it into f of x could be x cubed, g of x could be 3x minus 5. So then when I compose those functions together, when I look at f of g of x, it actually takes me back to h of x. So I'm taking function g, 3x minus 5, and I'm placing it inside of function f, which is x cubed, and we have done the composition. And so here is a kind of a thing to help you out. Basically, when you want to decompose a composite function, you look for an inner function and an outer function. So in the function above, g was our inner function, f was our outer function, and that's all you need to do. So for example 6, we're decomposing the function, and we're given that h of x is equal to 1 over x minus 2 quantity squared as a composition of two functions. So let's first find our outer function and our inner function. The inner function would be what we have here in parentheses. Let's go with that. So we're going to say that g of x is x minus 2. Our outer function is whatever we're left with. So once we get rid of this x minus 2, we only have 1 over x squared remaining. And there is our decomposition. We could have also done f of x is 1 over x, and our inner function could be x minus 2 quantity squared. In either case, f of g will generate the exact same value as what we have for h of x. All right, and then finally example 7. All right, sorry, I had to take a phone call. Let's get back to this problem here for example 7. So we have the number of bacteria in a refrigerated food is given by n of t is equal to 20t squared minus 80t plus 500. T is the temperature of the food in degrees Celsius. N is the number of bacteria. When the food is removed from refrigeration, let's see. Yep. Okay. Sorry about that, guys. I had somebody at the door. Even though I had a recording in progress sign on the door, they still decided to knock. Let's see, where was I? So when the food is removed from refrigeration, the temperature of the food is given by this function. T of t, and that's lowercase t, is equal to 4t plus 2, where t is the time in hours, so lowercase t is the time in hours. First of all, A, find the composition n of big T, little t, and interpret its meaning in context. So what we want to do for part A is we have n of t is equal to 20t squared minus 80t. And then we have t of t is equal to 4t plus 2. So all we have to do now for this function is do the composition, which would be n of t, and then lowercase t. So n of t of t. So it's going to look like that. So we're taking the function here in red and putting it inside the function that I have listed in blue. So we get 20 times 4t plus 2 quantity squared minus 80 times 4t plus 2 plus 500. We will simplify this. I get 16t squared plus 16t plus 4 minus 320t minus 160 plus 500. Distribute the 20 through the parentheses. So 20 times 16 would be 320 t squared plus 320 t plus 80 minus 320 t minus 160 plus 500. And somebody's knocking at my door again. I will get through this video. Okay, so we've made it this far. Now we're going to combine like terms and simplify our expression. I don't have anything else that I can combine with the t squared, so I have 320 t squared. We do see that the positive 320t and the negative 320t, that reduces to 0. All that we have left now is to combine all of our constants. Positive 80 and 500 is 580. 580 minus 160 is going to give us 420. So this is our composed function, and it says to interpret its meaning in context. So what this means now, our composed function, we can put in any time, and it's going to ignore the temperature because that is now factored into our problem by the composition of the function. So now when we put in a given time, we can determine the number of bacteria without having to know the temperature and without having to utilize two functions simultaneously. And we can put that into practice now with part B. Part B says find the time when the bacterial count reaches 2,000. So our bacteria count is 2,000. And if we want to know what time that bacteria count reaches that value, we have this function now, 2,000 equals 320t plus 420. So we're going to subtract the 420 from both sides, which would be 1580 is equal to 320 t squared. And 1580 divided by 320, I'll have to look that one up. That's going to be 4.94 approximately t squared. And then we take the square root of both sides. Now when we take the square root, remember that'll generate a positive value and a negative value. But since we're talking about time, time is never negative, so we're only going to look at the positive value. So taking the square root of both sides, we get 2.2. So t is approximately 2.2 hours. So 2.2 hours into this experiment, the bacterial count should reach 2,000 in quantity. And I believe that is it. There's not very many homework problems on here. I know it may look like a lot, but it really isn't. Only one word problem. This will be due next Thursday, which will be the 24th. So if you have questions, you start working on this, let me know. I'll be happy to answer them for you. I hope you guys are doing great, and I'll be talking to you tomorrow.